Welcome to the lecture on Introduction to Heat Transfer Phenomena. So, as we are going to have the study on the Tundis flow. So, in Tundis there is a flow of molten steel or any molten metal which is at very high temperature, and since it is flowing. So, we have studied about the basics of the fluid flow phenomena. Then also in that flow we talked about the turbulence, and we had some idea about how to model this turbulence. So, because of the turbulence certain extra terms are coming in those equations. So, how to model them. So, that we have studied in the earlier lectures. Now, we will have to have some fundamental understanding about the heat transfer phenomena. Because the heat transfer is an essential part of that process. Heat transfer will be taking place by different modes, and that affects the process, that affects the flow configuration also in many cases. So, we need to have the understanding about the heat transfer phenomena. Now, coming to the heat transfer, as you know, there are basically three modes of heat transfer, and that is conduction, convection, and radiation. So, as you know that whenever there will be a gradient of temperature will be there. So, when there will be change of temperature there in the body. So, there will be transfer of energy will be there from higher temperature towards the lower temperature side, and that is your conduction. Then we will talk about the convection, where because of the fluid motion or fluid in contact comes into picture. So, that time you have convection, and then you have the radiation. So, that is because of the electromagnetic radiation which is emitted by the temperature maintained at higher by the body maintained at higher temperature. So, you have three modes, and all these three modes are active in the case of the steel making process. For example, if you talk about a normal Tundis, so you have the inlet, and then you have the you may have the outlet. So, this is your inlet, and these are the outlet. So, what happens that the high temperature metal which is coming. So, you have a ladle here. So, from the ladle your high temperature metal will be coming and getting poured into the Tundis. Now, this will be striking at this point, and then it will be going and moving inside. So, they will be having contact with these walls of the Tundis. Now, these Tundis walls are normally refractory lined, but still there is heat transfer taking place. So, those heat transfer which is taking place from here. So, the heat transfer in between these places which take place there, and then also heat transfer which will be there at the surface because of the fluid motion. So, that will be the convection further, and then the heat transfer is also taking place from these surfaces. So, from the here the heat will be going out. So, they will be normally by the in the form of electromagnetic radiation. So, that is by radiation mechanism. So, all these three kind of heat transfer modes are there in the case of Tundis, and we need to understand, and we also will see that where it will be required in our case. Basically, when we try to solve the equations, so we will have the energy conservation equation that we have already seen in our previous lectures. So, we are solving for the temperature, and in that we need to supply these the boundary conditions, and we need to give that in what way the heat transfer is taking place. So, suppose from the inlet you will have to specify the temperature of the material or the metal which is going into, but then the heat transfer which is taking place from these walls need to be shown. So, you will have the heat flux which is there from these walls or from the top surface, they need to be provided. So, this will be the input to the model, and then we will get the we will have to solve the equation and get the temperature distribution inside the TUNDIS. So, coming to the conduction. So, the conduction is that when the temperature gradient will be existing in the body, so there will be energy transfer from the high temperature region to the low temperature region. So, this type of heat transfer is called heat. So, in the body itself you have when you have the temperature gradient. So, just like you can see, if you see this TUNDIS, if you have a TUNDIS and you have the there will be refractory lining. So, if you talk about the lining, now in this case this temperature is quite high, and this is close to, this is exposed to the external atmosphere. So, that is surrounding. Now, in that you will have the because of the temperature gradient there will be propagation of heat. So, there will be, that will be done by conduction in this, because through this material. So, that is by conduction. So, that is the conduction. So, you have a solid body, this one side is a heat temperature side. So, in the case of TUNDIS, the face of the wall which is in contact with the molten steel. So, that is having high temperature, and the external face of the TUNDIS, which is a steel cell normally. So, that is at a lower temperature. So, certainly in between you have the refractory material. So, there will be transfer of heat through that medium and through that material, and from the high temperature to the low temperature region, and this type of the heat transfer mode, that will be your conduction mode. So, in conduction normally we use the Fourier's law of heat conduction, and basically what has been seen, that the heat transfer which is there, it will be proportional to the temperature gradient, then area, and also the time. So, if you talk about so this is d theta is nothing but the theta 2 minus theta 1. So, if you have a region, that is this is the higher temperature side and this is the lower temperature side, you have this side the temperature is theta 1 and this side the temperature is theta 2. So, there will be flow of heat from this side to this side. Now, that will be proportional to what has been found by Fourier, that it is proportional to the temperature gradient. So, how much is the gradient, that is d theta, and that is d theta by dx basically. So, this is d theta by dx, this is the dx for an element. If you take dx, so this is the length dx. If you take x in this side, so dx will be a smaller part of it. So, dx incremental part. Then it will also be proportional to the area of which is there in contact. So, if higher is the area, higher will be the heat transfer. Similarly, higher will be the time, so for how much time it is the heat transfer is. So, if you calculate for higher amount of time, it will be more, there will be more heat transfer. So, then in that case that there was a constant of proportionality added, and that constant of proportionality gives you that is lambda, or many times we call it as a K also, that is the thermal conductivity of this material. So, this way we find this Q. Now, if you try to have for per unit area and also rate of the heat transfer, so we divide it by A and T. So, in that case Q will be becoming minus of lambda d theta by dx. Now, the minus sign, as you know, you must have the idea that we normally give this minus sign because d theta term is negative. So, because theta 2 minus theta 1, this term will be negative in this case. So, that is why we are putting it minus, so that you have altogether you will have the positive term. Now, what we need to do when we try to, if you try to see the Tundish, in that also we need to, so if you are modeling any Tundish flow, so in that case you need to have the dimensions of this part. Also you need to you can specify the temperature on this side and temperature on this side, and also you need to, so basically if the dimension is known and the temperature is also known on these two extreme sides, then d theta by dx will be known, and then if you know the k, so or lambda, so that is what is required. So, that way you can have the conduction heat transfer you can find in those cases. So, what will be required when you go to the modeling of the Tundish flow, and you are required to give the boundary conditions for the temperature or thermal boundary conditions on the wall. You need to specify the material of the wall. So, if you have the refractory, you need to provide the refractory material with the appropriate value of the thermal conductivity. So, that is what the there will be, the use will be for the thermal conductivity of the material. So, that will be varying for different materials, and you can have the appropriate value of the thermal conductivity of the material. So, there may be ceramics of different type, and you can have the thermal conductivity value from the literature for those values. Accordingly we try to model the conduction part. Now, coming to the convection. So, in conduction we know that we need to have the value of the thermal conductivity, and this is the property of the material, and that will be required to have the value of the conductive heat flux or conductive heat which is transferred, heat transfer by conduction. Now, heat transfer is also accompanied by the fluid motion. So, you will have this is your surface area A, this you have the surface temperature S theta S. So, and the Q is the heat flow, and your approaching flow temperature is QF. So, in that case what we see that we get the expression for the heat convected by the Newton's law of cooling. So, Newton's law of cooling tells that Q is basically equal to alpha times theta S minus theta F times AT. So, again you can have the expression for the Q, that is alpha times theta S minus theta F, and in this case we have the term that is the heat transfer coefficient, which is coming into picture in such cases, in the case of convection. So, you will have these values, and we are using this many a times. We also denote it with H in place of alpha. In most of the cases we also try to have So, heat flux what you see Q, it will be proportional to the temperature difference here, and you will have the values of alpha into theta s minus theta f. Now, what we need to know that when we talk about the convection, then there are two types of convection mechanism. One is the free or natural convection, and one is forced convection, which is induced by the external means. Now, in the case of free or natural convection, what happens that because of that, so that is basically induced by the buoyancy forces, and it is basically in those cases when there will be change in the density. So, in that case you will have the loop formation, or the there will be a convection current which will be generated because of those natural drop in the temperature, or because of the change in the density or so. So, that happens also in the case of Tundish, where it has been seen that in case of Tundish, when you have the temperature difference in the Tundish, and it is of the significant magnitude, larger magnitude. In that case, because of that, you will have a convection loop which is formed, and that will be affecting the velocity profile in the Tundish also. So, that is because of the buoyancy forces that is induced, and they may occur, and this free convection or forced convection that may occur with phase change, boiling, or the condensation processes. Now, if you talk about the the value of H, that is heat transfer coefficient, which is having unit of watt per meter square Kelvin. So, in the case of free convection, for the gases, you are getting the values as 2 to 25, and for the liquids you have 50 to 100. Whereas, when you have the forced convection, in that case you have if you look at the value of these heat transfer coefficient, it is multiplied 10 times as compared to that in free convection for gases. And then for liquids also it is going maybe close to more than 200 times, about 200 times. So, that is the heat transfer mechanism for, that is what is required, that is how the heat transfer is changed when you have the forced convection taking place. In the case of boiling and condensation, that is even more, it goes to 2500 to about 1 lakh watt per meter square Kelvin. So, that is how the heat transfer, you can see that how these heat transfer order can be seen to change when you have the different in different way your whether the convection is by free mechanism or by the force mechanism. So, in those cases you are having these values. Then you have another part is the radiation. So, radiation is again it is an electromagnetic radiation where it is emitted by the body as a result of its temperature. So, in that case what happens that you have a body which is at higher temperature. So, it will be emitting the radiation towards the body of lower temperature. So, that is the principle. So, that basically in terms of, so this flow which is going to take place, that is basically in the form of electromagnetic radiation. So, that is why it is called as the radiative heat transfer. Now, in case of Tundish, what happens that you have many surfaces which are open. So, you have the top surface of the Tundish where you have slag layer, or or so, which is also at higher temperature. So, there will be heat transfer taking place from that surface, because it is exposed to atmosphere, and that is slag is in touch with hot metal, and slag is also at very high temperature. So, they will be losing the heat to the surroundings, and that is done by the radiation mechanism. So, again here also you will have the similar process, but here the temperature the exponent which we use on the temperature, and that is different, and that is by the Stefan-Boltzmann law. So, that we will see. So, that way it is changing. So, whenever we are dealing with these thermal conditions, so in that case you will be asked whether you want to give a condition where there is radiative heat transfer or not. So, that you can accordingly you can supply those conditions. So, if you talk about the radiation heat transfer, it is basically described by the Stefan-Boltzmann law, and that is by the expression sigma b times theta by 100 raised to the power 4. So, basically that is for the black body. So, what happens that normally you have as you see that it will be a function of the fourth power of that temperature turn. So, you will have if you look at these material, you have a body. So, you will be absorbing, you will have incident energy, then you have reflected, and then you have transmitted energy. So, that way we also try to have the radiative heat fluxes, we also try to provide on the on those surfaces from where the radiation has to take place. Now, after that we need to know also a few terminologies, like you have the hydrodynamic boundary layer and the thermal boundary layer. So, the hydrodynamic boundary layer will be defined as that region of flow where the viscous forces are felt. So, as we see that you will have a region close to the wall where you will have the viscous forces are in dominance, and that layer. So, you will have the formation of the hydrodynamic boundary layer. Similarly, you will have the thermal boundary layer also, and this is that region where the temperature gradients are present in that flow. So, you will have the temperature gradients that will be seen in that thermal boundary layer. Now, these temperature gradients would result from the heat exchange process between the fluid and the wall. So, that is what we discussed, that you have the fluid and the wall. So, you will have the heat exchange process taking place between them, and because of that these temperature gradients will be resulting into. So, normally there has been the description of the hydrodynamic boundary layer and thermal boundary layer by dealing with the Stokes first problem, and where it is dealt that there will be flow around the wide flat plate, which is suddenly moved from rest to a constant velocity, and then what will happen that the fluid which is adjacent to the plate will be moving with time. So, once you are moving, now that layer, which is this layer will be called as the hydrodynamic boundary layer, and the velocity of the fluid will be decreasing in the direction normal to the plate. So, as we know that it will be decreasing in that direction normal to the plate from V on the surface to the of the plate to 0 outside that layer, and the thickness also is found to be increasing with time by this expression. So, delta H will be 4 of Vf into T raised to the power half. So, that way you are getting this nu F, and this is nu F is nothing but this is kinematic viscosity of the fluid. So, if you look at the development of the, this is nu F. So, this is if you look at the hydrodynamic boundary layer formation. So, they are they are very much the growth of this hydrodynamic boundary layer, they are a function of this kinematic viscosity mud. So, in that case it is a measure of the momentum exchange of the flow. Now, in the same manner you can have the thickness of the thermal boundary layer also on the flat plate, and that is governed by Kf, the property Kf, that is your thermal diffusivity, and that is lambda f by rho f Cp. So, it is also sometimes in some terminology you will be as K by rho Cp. So, K is nothing but lambda f, that is thermal conductivity, then this is rho, and this is the Cp. So, this rho is density and this is the specific heat at constant pressure. So, that way we try to have these thermal boundary layers also. So, that will be governed by these processes. Coming to the different types of the dimensionless numbers which we will be required, which we will be coming across in our study, and that will be first is the Prandtl number. So, this Prandtl number is the ratio of the kinetic viscosity, that is nu f, to the thermal diffusivity Kf. So, that way we define this nu f by Kf. So, it is basically the direct measure of the ratio of thickness of the hydraulic and the thermal boundary layer, as we have seen. So, it will be measuring the ratio of the thickness of the hydraulic and the thermal boundary layer. You have another relevant dimensionless number, that is your Smith number Sc, and this Smith number, it is the ratio of the kinematic viscosity to the diffusion coefficient d. We have already seen earlier also. So, in that case also you take the ratio. So, that is your many a times we have the turbulent Smith number and all that. So, this basically will be talking about the ratio of the kinematic viscosity nu f to the diffusion coefficient d, and this is the Smith number. So, these are these are the apart from that you will have there are many other numbers which will be coming into picture, like when we talk about the natural convection. In that case, as you know that that deals with the numbers like Grashof number or so, and when we deal with that we have already seen that there is another number, that is Tondes-Richardson number, that also is used many a times while we deal with the thermal analysis of the Tondes flow. So, so these I mean these terminologies will be useful while analyzing the output which we get by after post processing operation. So, in those cases you can have the idea of the value of these parameters or these numbers, and by that you can compare the processes or compare the different cases. Apart from that we will have also we will be dealing with certain phenomena like the phase change or so, that is what we had seen earlier. So, you need to also see that how there will be you will have the different models which talk about the phase changes during the heat transfer. So, in many cases and mostly in metals, when your temperature goes below certain limit, so that starts changing to different phase. So, the liquid phase will be changing to the solid phase, and in that case if that phase change is taking place, many a times we have the change in the properties when we are there is change in phase. So, you will have the conductivity values or heat transfer coefficient values which is used, especially the conductivity values will be different when we have the phase change taking place. So, those also need to be looked into, so that will be governed by the material properties also, because that will only say that when the temperature becomes lower than that, you will have basically the change of phase from one phase to other. So, you will have different equations which will be talking about the transformation of one phase to other in a gradual manner, and then how it will be affecting the heat transfer or fluid flow in the domain. So, these things may be used by us in our lectures to come when we deal with that particular situations. Thank you very much.